neural light transport for relighting and view synthesis. In this work, we present a unified framework for directional or image-based relighting, view synthesis, and both tasks simultaneously. We do so by interpolating the 6D light transport function, a radiance function of the location on the surface, the incoming light direction, and the viewing direction. We capture the data using a light stage. If we query the learned function and novel viewing directions, we are synthesizing new views of the scene. If at novel light directions, we are relighting the scene. If both directions, we are performing simultaneous relighting and view synthesis. We approximate the light transport function with convolutional neural networks. We embed the function into the UV space, computed from a geometry proxy. Using the UV space is key to handling viewpoint changes. We provide light and viewing directions in the form of cosines with the normals, and ask the network to predict the RGB values for each texel. The predicted texture map then gets resampled back to that camera's perspective, and then compared against the ground truth image. We also feed in a physically correct diffuse space rendering, so that the network doesn't need to relearn the albedo and harsh shadows. There's also a skip link from the diffuse space to the network's prediction, to explicitly tell the network to focus on learning higher order light transport, such as specularity and global illumination. Finally, we have an observation path to additionally encode what the non-diffuse residuals look like for neighboring observed lights and views. Such observation features get averaged and then concatenated back to the query path for it to decode the query view residuals. Here are the results for directional relighting. These are the light locations and the corresponding images used for training. Our prediction adds specularity and global illumination effects to the diffuse space. It also compensates for geometric inaccuracy visible in the diffuse space. It is also more than just copying from the nearest neighbor, as seen from the different shadow boundaries. Here are more directional relighting results. Note the light-dependent effects, such as facial specularity, and the specularity on the lady's jacket. Also, the cast shadows. By linearly combining the directional relighting results, we can relight the person according to an HDRI map. Here are some results. And some more. We can also synthesize novel views of the scene with view-dependent effects. Here are the camera locations and the corresponding images used for training. Now we are rendering the person using an arbitrary smooth camera path. At scene, it doesn't really work to just render the captured geometry assuming a Lambertian BRDF, or just copy from the nearest neighbor. Here are more view synthesis results. Note the view-dependent effects, such as facial specularity. Some more view synthesis results. We also compare our method with deferred neural rendering in view synthesis. Note that their approach doesn't support relighting, unlike ours. We show how our model simultaneously relights and synthesizes new views of the scene. Here are the cameras and lights, and their corresponding images used for training. At test time, the light first follows the camera exactly in doing a 360, and then diverges into a spiral path. Here are more results for simultaneous relighting and view synthesis. Thanks for watching. Visit the project page for more.